Hello and welcome to our webinar, Modeling and Simulation with JuliaSim. I'm Jay Jagdish. I'm a part of the marketing team here at JuliaHub. Let me take this opportunity to wish everybody a happy Valentine's Day. Thanks for joining us today. Today, Chris will be talking about how state-of-the-art SciML is being transferred to industry through JuliaSim. A little background on Chris. Chris is the Director of Modeling and Simulation at JuliaHub. He's also the lead developer of the JuliaSim project. He's well known for his work in scientific machine learning as a research affiliate at MIT. Please take advantage of the session to ask questions and participate. Please enter all your questions in the chat. Chris will answer them as they come whenever he finds time to pause. Over to you, Chris.
Yep, thank you very much. So today what we're going to do is we're going to go through JuliaSim. We're going to kind of go through its world. What is scientific machine learning? How is this all coming together? And then how is this being brought to industry through this product that we've been developing over the last years? So, this is going to be the agenda here. We're going to start with just, what is Julia, in case you're not familiar, and then go into what is JuliaHub, the company that we've developed around Julia. And then what is scientific machine learning for, because it's one of these new, scientific fields. You might not have been, as aware of it. I want to show all like the cool things that are going on in scientific machine learning, and then show how you can do scientific machine learning with JuliaSim. So before we even get started, I want you to know that all of these materials, all these things that I'm doing, the code for this is all online. JuliaSim is ready for you to start, take a look at the docs, start looking at this. If you're interested in using it, come talk to us. We can get you access. The documentation is live for you to start looking through and say, hey, what are all the cool things I could do with controls? Look at all the model predictive controls tutorials, optimal controls tutorials. All of this is right there, accessible for you to start looking at it and start using it if you ask for access. So please start looking at this in detail, right? This talk will be at a high level to kind of introduce everything, but if you want to dive in, we're ready, to come talk to us. So let's start by talking about the Julia programming language. Right. So the Julia programming language started in 2012. It's this language that was developed at MIT to solve the two-language problem. So the purpose of it is so that way you can have a code that is as simple as Python, but run as fast as C. And from that premise, we've been able to develop a whole lot of technologies on Julia, right? Because the moment you get that performance kind of for free, then you start being able to develop a lot of libraries very quickly. And this is where a lot of projects such as Pumas and SciML, that's when these were developed using the Julia programming language. So what we've really done though is we've noticed that Julia has had a strong point around the modeling and simulation area. So this area of modeling, control, model and physical modeling, biochemical modeling, all these areas have kind of been Julia's biggest strong points. So we started to develop a whole bunch of proprietary software around trying to ensure that industries can start to adopt these pieces that we've been have been flourishing. And this is what JuliaSim is. And so JuliaSim started in 2021, and it's now been starting to be used in a bunch of different industries for this exact purpose. Julia, at this point is not, too new. I mean, it's a newer programming language than many, but it's still already in the point where you have 38 million downloads of the language, 57 form views in a given year. So it has quite flourished with this kind of exponential growth over the last few years, especially with the pandemic. And so with the Julia community being so thriving and lively, what we've really been looking into is how do we begin to, not just change, one scientist's workflow with, a language, but how do we make it so that way, how do industries begin to adopt these tools, right? And so what I'm going to talk about is how, some of these examples came into play about, some of the companies that we've partnered with. So this brings us to JuliaHub, right? So JuliaHub is the company that is built around this cloud compute platform, also named JuliaHub. And the goal of JuliaHub is to make it so that way it's very easy to do cloud parallelism and integrate with all of these different tools that have been developed in Julia, right? Since Julia is about high performance computing, Julia is about performance, right? One thing that goes hand in hand with performance is parallelism. Now, not everyone has, a 1,000 core computer sitting in their backyard or a nice, GPU like, But what we can do then is we can bring this to everybody. We can make this open, we can make this accessible, so that way you can sign on to JuliaHub.com and get these materials as needed. So these are all developed in a way such that you go to JuliaHub.com, right? I can click over to here, JuliaHub.com. And what you'll find is that you can just open up, say, the Julia IDE. You can open up a JuliaSim IDE, or you can open up these Pluto notebooks, and these are accessible in a way that can use GPUs, thousands of compute cores, and parallelized for these high performance applications that Julia is so centered around. So this is the company, this is the purpose of the company JuliaHub, and it then ties together all the features that are required for these kinds of live deployed applications with parallelism. So things like using a Kubernetes to be able to scale jobs and scale the amount of cores required. It has an entire data sets type of feature, so the ability to be able to handle data sets that are larger than the memory of the machine that you're on, to be able to do these big data, hundreds of gigabytes kinds of calculations. It has a private docs and package registry. So if you have a company with hundreds of users, it can manage the way that you are developing private packages and depending on one another. And it has a bunch of different interfaces that Julia users are interested in or tend to use, like VS Code and Pluto, and there are actually more to these coming in the near future. So JuliaHub has been this foundation, but what we've been doing with JuliaHub then is we've also been developing domain-specific applications on this cloud compute platform, right? Not just the cloud compute itself, but also tools to be able to do pharmaceutical simulation, circuit simulation, and here today what we'll dive into is the physical simulation with JuliaSim. So if you want to know more about JuliaHub itself, some of these features like scalable compute, data sets, package search, the ability to host notebooks, right? I kind of show here that you can give someone a link to a live notebook that they can just begin to change numbers on their own, and be able to change the plots on the fly. If you're interested in more of these features, there's actually going to be a webinar coming up on February 27th that will go into all these new features with JuliaHub 6.0. So, get in touch, follow our newsletter, and that will give you more information on all of these features that I just mentioned. And they'll go into, how do you make use of Julia to, say, launch a GPU job with, get you an A100 and be able to use some of the, the latest hardware. So now what I want to do is I want to jump into SciML. So what is SciML and how does it fall into this whole story for getting us to JuliaSim? So SciML is one of these core pieces of the Julia ecosystem. Some of the most starred, some of the most used packages in terms of downloads. And the reason is because it was built on this foundation of high performance numerical solvers, right? So every time you do modeling and simulation, you need differential equation solvers, you need optimization, you need nonlinear solvers and all these pieces. And these got really popular because of the speed, performance, and robustness that they tend to afford. So, these are a few benchmarks that I would show in another talk. Go search for JuliaSim on YouTube, and you'll find all sorts of talks that talk about exactly these kinds of details, about how it's, 100 times faster than DSolve. And these talks will go into exactly the details about how that was achieved and how Julia was essential for that. But the key behind what SciML did, right, somewhere around 2019, 2020, there's kind of the shift within SciML of not just trying to be fast solvers, but also trying to integrate machine learning into that whole world. And this was scientific machine learning. And, we are one of the groups that really kind of pushed forward this domain, where the idea behind it is to mix modeling and simulation. So say biochemical models or physical models, to mix that with the data that we have, so instead of trying to do machine learning that is just purely data driven, and then say, oh, we have an engineer that's doing something that's purely model driven, what we would really start to look into was, can we make our tools combine the machine learning with the modeling and simulation to try to achieve some kind of best of both worlds, right? Of course, there's going to be some trade-offs as well, but can we use the ideas of both to kind of go forward in a new direction with simulation tools? And one of the key ideas behind that came out of this was the universal differential equation, right? Auto-completing models is kind of this idea of, can I type in a model and give it a bit of data and let it kind of do the Google thing where, it completes the sentence for me, right? And this is where we went with a universal differential equations. And if you're interested in this, you can check out one of the talks that goes into a lot more detail, or the manuscripts. But basically, the core idea behind it is you can augment known models with unknown equations, like using neural networks, and then you can use that to be able to symbolically discover what you didn't model. So given this model and given this data, if I know that the two are not connecting well, then, well, what am I missing? Am I missing that air friction needs a quadratic term? Am I missing that, I didn't model, am I missing a chemical reaction in my system? What we showed throughout a whole bunch of the different research was that this was possible with scientific machine learning. And many researchers around the world began to use our tools to be able to, demonstrate these kinds of capabilities. So, here's one really nice example that has you can go to this astroinformatics workshop and actually find the Jupyter notebook that is behind doing this example, where the researchers presumed that all that we knew was Newton's laws, right? So this is Newton's laws in a rotating frame, but there's two black holes moving around, and there's the measurements of the gravitational waves from LIGO. And what was done here was taking the idea that Newtonian physics is approximate. Can we automatically extend Newtonian physics to have its relativistic corrections such that we can then predict where the black holes will be, right? Because black holes are moving fast enough, so that way you need to have the relativity. And what they're able to show was that the scientific machine learning approach, right, assuming Newtonian physics is close enough, augmenting it with these Fs, which are neural networks, they showed that you can basically make it so that way you can learn enough relativistic dynamics such that you're able to predict well in the future. The training data is the black. The prediction is the orange, the real data is the blue, and in general relativity, this would be a bad prediction because it's only 3 digits correct, but in machine learning, it just extrapolated out of your data set in a way that's pretty wild, right? And so, what we started to see was that there's a lot of these cases where this kind of scientific knowledge really helps with the modeling process. Here's another example just pulled, from, there's hundreds of people who have cited this at this point. So here's an example where researchers use earthquake safe building as an example to demonstrate that universal differential equations could find a improvement, right? Here's some research that we've worked at CMU. They developed models of batteries, but what they really wanted to understand was, how do I define new materials that would give me batteries that would degrade slower, right? And we don't really have a good physical model for how batteries degrade. We know how batteries work, but when it stops working, why did it stop working is a big question. And so what they did was they used universal differential equations to find a predictive model of how battery degradation works. So that way the materials discovery process can find materials that are able to stop this degradation, right? And so these are some ways in which scientific machine learning has begun to be used. In fact, if you're interested in this topic, you can go to the open source SciML. There's improving coverage of automatic differentiation over many, many, many different solvers in this ecosystem, right? It covers linear solvers, nonlinear solvers, differential equation solvers, optimization. And you can go to one of these other talks that I've given and see, the details behind how there's 50 different adjoint methods, and what do they all do differently? What are the trade-offs between them? Some are faster, some are more stable, et cetera. So there's an entire ecosystem with tons and tons and tons and tons and tons of choices, right? And that's really the key to this open source ecosystem. You go there, and if you want to look at any detail, all the code is there. You can change any detail that you want. There's pretty much every method that we can do. And we're really just trying to, in that open source ecosystem, cover every possible method we can, right? It's all about choice and the ability to modify everything at will. But what we found is that, while they can give you this top-notch performance, right? We're getting things that can outperform JAX by about 10 times with new GPU solvers. The issue is that this is very complex, right? We know that the open source ecosystem is complex, and that's almost by design because we want to make sure that it has every option available, right? And so, this allows you to be able to take the tools that are open source and build something on top of it that has the utmost, the utmost performance because every option is available to you. But then this leaves something open, right? So, do you need to know all these adjoint methods? Do you need to, know every optimizer in this list? If you really need to get the #1 performance and if you are building your own tool from scratch, maybe. But for most people, can we get 99% of the way there with something that's a lot more automated? In fact, can we make it so automated that we can make it accessible from a graphical user interface? And this is the question that we've been really starting to ask and answer with JuliaSim, right? This is about the tech transfer. So we know that scientific machine learning works at this point. There's hundreds of citations that are showing, yes, don't do standard machine learning. This does help out over the previous ways. But how do we translate this to industry use, right? And another way to state this problem is, how do we make it so that way you don't need a math PhD in order to do scientific machine learning in practice, right? That's something that the open source doesn't really focus on, because it tries to just make sure everything is available. But if you have recently hired a few mechanical engineers and they're not familiar with scientific machine learning, how do we give them a tool so that way they can do enough of this fast enough without spending 5 years learning about it? And that's really what the true goal of JuliaSim is, right? And so I think that this is like the best way to kind of understand where it is. So, the open source SciML, you see the whole code, and choice is the #1 goal. It's kind of like, we almost think about it as like Arch Linux, right? If you're someone that doesn't know what Arch Linux is, then, you probably don't want to be in that group, right? It's really about, you can modify every little detail, build whatever you want, go ham at it. But JuliaSim is really looking at this problem of, well, we need to build a set of tools that subsets to, let's make SciML work in such a way so that way it works the first time, just do it for me, auto-generate reports, verifiable on a secure hardware, kind of like what you would think about with Red Hat Linux versus, a kind of more retro or hipster, Linux repo, right? So that's really, it's really enterprise focused to make sure that, it's like we're looking at the things that we can, really make sure work, and focus on the things that require the least tweaking. Maybe it's not going to be the #1 method the whole time, because you can find some other neural network that you can tweak some parameters. But you know what? If it gets 90% of the way there, but it gets there without tweaking, that's probably what we need, so that way we can use it for an industrial purpose, right? It's about robustness. And so this is what brings us then to JuliaSim. So JuliaSim is this product developed within JuliaHub, which is explicitly for bringing scientific machine learning to industry, right? And so everything is about this modeling and simulation process and how it connects to data. So this is like one high-level way of explaining what we have. You can go to the JuliaSim documentation and see that there's many different modules. But another way to look at this is the question of, do I have models and do I have data? If you need to build models, there are some pre-made model libraries, which I'll be discussing in a little bit. If you have data but no models, you can make use of things like the digital twin generator in order to build a model from this data and then use it along and co-simulate that along with the other models. If you have models but no data, you can do things like build a surrogate, a machine learning analog of your model, to then be able to accelerate it. And last but not least, if you need to match models to data, you can use something like the ModelOptimizer, which is able to find the parameters of the model that will fit the data, or be able to find how to extend your model, do this universal differential equation process in a way that's a lot more automated than what's out there. So kind of
Chris,
yeah.
Someone was wondering if they can find the code to be able to run the models that you're describing.
Yeah, so just to kind of highlight this, what you do is you go to help.juliahub.com. If you go to help.juliahub.com, it'll bring you to the entire documentation of JuliaHub. You'll see at the top here, you'll find the ModelOptimizer, controls, and these will bring you to the tutorials. And what I'll be describing will be examples either pulled from the tutorials or examples pulled from actual industry use cases. Of course, the industry use cases, we can't share all of them, right? We can't share the proprietary model, but we can share tutorials that are written to kind of mimic, how you would do these analyses. So. Yep. And so another way to kind of anchor in your head what the different pieces that we have as part of JuliaSim is to look at a full workflow. So let's say you're an electrical vehicle engineer, right? And you want to optimize the energy efficiency of a new HVAC system. Well, what you can do with JuliaSim is you can use the tools for, say, importing an FMU to be able to take an FMU of your HVAC system from, say, Dymola or some other FMU compatible tool. And you can hook that into one of the battery models that we have. So Petline, for example, is a battery model that we have now. I'll be describing later some of the more developed battery models that we are developing. What you can do is you can begin to use our modeling toolkit tool to be able to hook these together. And once you have this composed simulation, you can start to ask, real analysis questions. Well, in order to ask some analysis questions, and maybe your model's too big, right? If your model's too big, you might want to use a surrogate trainer to first accelerate the model with machine learning, then bring it to the model optimizer, this accelerated form, to make it match your data. And once your model is calibrated with your data, you can say train a controller, so that way you find what is the control policy that optimizes the energy efficiency according to the properties of this HVAC plus battery system, right? And then you can start to bring this to the field with some of the tools that we're developing. Be able to use the fact that JuliaHub has a online API, and you can have it query. You can have it streaming new data to the cloud compute, and it'll just stream back what the results are in terms of control policies or new controller techniques, right? So this is kind of like a whole workflow from model to car kind of idea, right? And all these pieces are part of this JuliaSim platform. So let me kind of start to deep dive into a few pieces, just so that we can kind of get a feel for what they're all about, what results have they demonstrated, and how are they being used in different areas. So here I'm going to look into JuliaSim surrogates. So just to highlight it, this is what you'd find at the JuliaSim surrogates place. And this documents how you do things like surrogatize using different neural network techniques, right? Now, the key behind what the JuliaSim surrogates module does is it takes a model that you have, say either an FMU from Dymola or a modeling toolkit model, any kind of these acausal models or causal models. Simulink FMUs work as well. It can take one of these models and generate an equivalent model to that, which is a machine learning neural network approximate, right? It's not going to be exactly the same. It's going to have some error in the difference, but it's going to be an emulator of the original model. And the key behind it is that this emulator will run a lot faster. In fact, we've shown that, I'll show some proof behind this. We've shown that generally thinking about it as 100 times faster is a relative benchmark. And so, what you can do then is you can say, well, if I have a very refined model and it takes, days to run, if I need this to go 100 times faster, and I'm okay with having a approximate version that runs at 1% error, you can run it through the JuliaSim surrogatizer. And what it will do is it will give you back a equivalent dynamical system model. It presents itself as a differential algebraic equation, just like any of these other acausal models. And you can use that then as that portion. So we actually had an example where we did this to an air conditioning unit, and we use the accelerated version to be able to find what building design would be faster, right? Why would we do that? Well, because this air conditioning unit is usable inside of many different building designs. And so we accelerate the air conditioning unit once, and then we allow for building different models around it. If I use this air conditioning in this building, and if I use this air conditioning in this building, which of them are more energy efficient? And in each of these cases, because the air conditioning unit was the most expensive thing to simulate, this gave a speed up in practice. So this sped up the simulation by about 100 times. And then it gave about a 570 times acceleration total over one of the other models that we had compared it to. And then when we put this into the global optimization loop, that made the global optimization about 340 times faster. Now, after we found a global optimization result, we went back to the original model, right, to be able to say, hey, is this a good result on the original model, just to double check, right? Because remember, the surrogate does have a bit of error introduced on it, but this kind of shows a, machine learning integrated workflow, right? That you can use the machine learning model to start to do expensive activities. And once you found the solution of the expensive thing, you swap the original model back in. And so JuliaSim allows for doing this quite simply by using the tools described in the JuliaSim surrogates module. Now, there's a few different types of surrogates. I think that the two that are most interesting to point out here are the full model versus the component-based surrogate. So the full model surrogate is focused on this, the full model surrogate is focused on this kind of idea of, okay, so I have a whole cost function, right? So let's say I'm trying to do a optimization of a very specific dynamical system, and I know that I'm not going to change this dynamical system. For example, if I have a biochemical reaction model, or if I have a model of the heart, I'm going to be using this heart model for the next few years. So what I can do is I can, build a surrogate of this full model. This is the one this is a very robust, fast thing, and a lot of the docs are focused on this today. One of the things that we're going to be releasing more on in the near future, though, is this component-based surrogate, which is more about the problem of, so let's say you have one box inside of a simulation. So if in kind of in Modelicus speak, you call it a component. In like causal model speak, you'd call it a block. As part of a block model. Can we take what we can do with this is we can take one block and build a surrogate of that block. This is what I described with the air conditioning system, right? Where you can make a surrogate of the air conditioning and then change the building around it. This does take longer to train, but it's reusable in a lot of other circumstances, right? So if you have one specific air conditioning unit that you're, or a refrigerant type or something that your company tends to use a lot, you can build a surrogate of that component and then begin to reuse it in all of your downstream models. And then everything downstream will see that acceleration. You need to make sure that you perform the right uncertainty quantification, which is why we have a lot of tools for visualizing the uncertainty and the error of the models, just so that we can get a full quantification of this. Though this allows you to kind of give a reusable speed up in many ways. So you train once, use everywhere kind of thing. This one on the left is what a lot of the documentation is focused on today, though I'm just kind of giving you a feel that, there's a lot on the component-based surrogates that you'll be seeing and hearing about within the next few months. And what we
there's the question,
yep.
is can you combine non-ML statistical or similar model with a surrogate model?
Yeah, and I'll actually show I'll show an example of this in a bit, right? Because I was mentioning how physical information really helped with the the cracking of the code in a few problems, right? The whole SciML idea. So I'll actually show an example in a bit that did not work until we brought in some SciML elements. So yeah, wait about 5 slides, I think it is. I'll mention when it is. But yeah, so with the surrogate trainer, right? What can we actually build surrogates on? Well, we can use the tools from SciML. So if you're a Julia user and you're building models in Modeling Toolkit, then Modeling Toolkit is one of these, is the acausal model that we allow things to be built off, right? But we also have a way to be able to integrate any model that comes from FMUs, right? So FMUs can come from SPICE models. If you're into circuit modeling, we've done this on Modelica models. We've done this on models from Simulink. We've actually made use of pure data as well. So if you looked at the latest version of the documentation here, you see that we can actually generate a physical approximate using pure data. As shown in this tutorial, right? And so, we can use many different sources to be able to generate one of these components that you can then build a surrogate from and co-simulate it with other simulation pieces, right? So, if you're interested in a type of simulation that's not in this list, feel free to get in touch and we can look at integrating more tools into this. But we've covered quite a few bases that we've heard from before. Now, I mentioned the 100 times number, right? How did I get to that? Well, we've had a bunch of different research articles, peer-reviewed research articles that showed that these surrogates were able to achieve these speeds. These are all the speeds that are given at 5% error accuracy, or some 95% accuracy, right? And so here, for example, was what we showed on Sky 130 inverter. So these are circuit models. These are quantum circuit models. So everything about in the same range. Then we had other papers that showed this on HVAC systems, building design, power grids, system pharmacology. And at some point, we just kind of go, okay, this is probably around the right number. As you can see, it's not always 100 higher than 100, but it's always in this kind of range of like 50-ish to 100-ish, right? I even have more examples, right? So there's a scalable building model that had, a bunch of rooms, 20 rooms in a row, and we showed that it hit 80% or 80 times, right? So there's so many different examples of that. So let me actually get to some of these questions here. So once your surrogate is trained and you're using it for faster inference, is there a way of ensuring that the model is performing well without having to compare to the original expensive simulation? Yes. So there is a way. I don't have this visualization booted up, but if you look at one of the other webinars that we've gone into so for example, look at the webinar on FMU Accelerator. It goes into using this surrogate dashboard to tell you which parameter ranges have the most error in the least error for the surrogate, right? So we have a way to be able to dig into this high dimensional space and be able to tell you these areas of the surrogate is where it's trained best, these areas is where it's trained not the best, and then you can then use that along with your analyses of your simulation to kind of see, are you in a zone where the surrogate is more trustworthy or less trustworthy, right? In order to get like the final value, the final data point, you do need to make sure you do a comparison to the original simulation, but the visualization kind of puts you in the right ballpark. So yeah, very great, very great question. Another question, is there a short course in component modeling? There is not a course in component-based modeling, but that is a very good question. I will definitely take that to heart and think about possibly making one in the near future. I will mention that there is a short course in controls modeling with Modeling Toolkit. Frederick has been running something on the YouTube. So if you look at the JuliaHub YouTube, you'll find, I think, 4 or 5 videos on using Modeling Toolkit with JuliaSim Controls. So that's a good starting point, though it does not go into the component-based modeling part, and we definitely can extend it. So Frederick's course, I believe, has 6 more videos coming, and after that training series is done, this sounds like a very good idea. Is there a non-pro version of FMU export from MTK for researchers? So there will be a free tier version of JuliaHub that will be launching soon. Get in touch as an EDE researcher once that's available. Then we'll be able to get you access to that, and you can use the FMUs module that's part of JuliaSim surrogates to be able to generate that. So that should be fine on the free tier. The free tier will not give you the biggest compute. You can't do the biggest parallel compute, but if your goal is to take a Modeling Toolkit model, generate an FMU from it, that should be possible from that. So be aware, be on our newsletters and stuff. Listen to watch for the words free tier. And so very close to answering that other question too. So a lot of what we've done with the Julia and SciML and our simulation stack has been focused on performance, right? So we actually very recently with a Formula One team demonstrated that we can get about 10 times performance directly on a finite element model, where actually the interesting thing about this was the model that we developed actually had twice as many nodes for the finite element model than the original one. And because of the cubic scaling of the finite element method, this actually would come down to around 100 times. But this kind of shows that in practice we're starting from a place that has a lot of performance, and these surrogate models are really extending that performance even more. And then finally, to the example, so we showed with this same Formula One team, right, that we can actually generate a machine learning model that could take the speed over ground sensor from the car and use track data that is run during practices to be able to predict what its location, angle, and on all these data from just the speed over ground sensor. Now, the key here is that this is one of these methods that's a physics informed kind of learning model, right? So this is Koopman siren, and it's also using some embedded physical law. So we actually put in some of the physical knowledge directly into there, and we'll have a future webinar that will kind of go into a lot more detail on what's kind of done with this method. But you can see the pure GP. So this is a Gaussian process model, pure machine learning model. the way that I would say it is, you don't want to be in that car. But it's really just an artifact of the training process, right? That this is something where the laws for how momentum is derived from velocity and position over time and such. These are hard coded, but also then extended with something similar to a chemical reaction neural network. We'll mention that in the future, but it's using a very specific technique that has some of the equations hand-coded, some of the equation forms being matching what is required for, say, conservation of momentum, conservation of energy. And what you get out of that is just something that gives you a lot more plausible of a result. And so this is something where, the one on the left is able to not only be doing faster predictions, but also being able to give more accurate predictions. And this accuracy thing is really where scientific machine learning helps out. Right, it's this regime where we had data, but we didn't have enough data to be able to make it perfect, right? But prior scientific knowledge was able to push it along. And in fact, we know that it is the SciML aspect that did this, because when we first, attempt number one was just slap a standard machine learning model on it and see what you get. We didn't get anything better, right? This is really the scientific knowledge embedded in it was required to be able to hit this result of being able to have that accuracy. So that's just about the surrogates and the digital twin generator. So we have the ability to either take a model and generate a machine learning approximate of it, or be able to do this directly from data. And some of the newer techniques that are not in the documentation yet, but as shown, will be coming out into the documentation rather soon. These make use of embedded physical knowledge, where you can give it certain equations. So you can say, like this observable is defined, this using these equations. And you could also say, what are the constituent types of equations that are in here, like exponentials, logarithms and such. And it will use that to be able to build a neural architecture that is more specific to that domain. But now I want to go into one of this next pieces here, which is the model optimizer. So the model optimizer is about quickly taking models and calibrating them to data, right? So you might actually be familiar with some of the tools that we have in Julia open source, right? In fact, things like DiffyQ Flux and DiffyQ Sensitivity, these are very popular tools, right? And people have, there's many different people who post a lot on discourse about how do you make use of this for lots of examples, right? But what we found over time is that, a lot of people don't want all the flexibility, right? This has all the flexibility in the world. And so sometimes in order to, say, do something that is difficult, you need to go into the tutorials where that tells you about, how do you avoid local minima and hand code some of these more difficult strategies, right? But, what we were looking at was, can we make it so that way, given the symbolic form of your model, can we guess what is going to be the best way to be able to do this and do all the splitting that's required, right? Can we automatically split your model across time and do a multiple shooting technique, and then, change the loss function such that it emphasizes one value more than another, do some hyperparameter tuning automatically, right? If we have parallel compute, we can do all this, just by spawning jobs. And really, this is what the JuliaSim Model Optimizer is about, making it so that way that calibration process can use the best techniques and try as much as it can to make sure it's robust and gets the correct answer, the first time, every time, hopefully, right? We know that nonlinear optimization is a very difficult problem, but this is the piece that, is really trying to aim for that, getting as robust as possible. It has a lot of techniques that are kind of different from just what is out there in the open source space. One of the pieces that it really focuses on is virtual populations, where a way to understand what virtual populations is about is it's the characterization of global optimum. So let's say you have a model that is very overparameterized, right? You can't tell me that you've never had that before. If you had a overparameterized model, then maybe increasing beta a little bit and decreasing alpha also gives you a solution, right? But if there's different parameterizations that also fit your data, what we really want to do is, find all of the different fitting models. We want to find all the different fitting parameters. And then we want to be able to run our analyses on all of these fitting models, right? We want to be able to test new designs with respect to this known uncertainty in the fitting process. And that's what virtual populations lets you quantify. It lets you quantify the uncertainty with respect to the global optimization process. right? So that way, if you do have something that's unidentifiable, you can at least kind of know how much of an effect that uncertainty is imposing on your downstream analysis. This is something that is quite unique to the JuliaSim ModelOptimizer, and we plan to have a few more webinars in the near future that kind of showcase how this can be used to be able to improve uncertainty quantification and the generation of robust controllers. So one place where the virtual populations has been seeing a lot of use, in where people have not that much data for very big models, is of course the pharmaceutical industry. We've worked with Moderna, Pfizer, and Sanofi. I think that each of these have case studies on our website that go into more detail. One case that we kind of can look at is the cardiac model that we did with Pfizer, where actually at one of these pharmacometric conferences, we were given an award because these model optimizer tools were able to give about 175x acceleration over the way that they were doing the optimization before. It was 15 times in just doing the pure optimization just with CPU, but then when we slap it onto GPUs, then the bells go rolling and everything flies, right? So, and there'll be more on this GPU acceleration actually coming out rather soon. If you want to read some papers that's using the DiffyQ GPU tools along with it's using the DiffyQ GPU open source tools along with the JuliaSim ModelOptimizer virtual populations analysis. So, once again, all of these things from SciML, they connect and reuse and reduce, reuse, recycle with what we're doing with JuliaSim. So that's about parameter calibration, and we'll have a few more webinars that go into some details of some of the new algorithms in there rather soon. But I do want to make sure that we have time then to go into this control systems. So JuliaSim Control, right, is really about trying to span this spectrum from simple to advanced controllers, right? And so the key behind it is, a lot of people today do linear controls analysis, right? If you open up a lot of things like Simulink, a lot of people are doing things like, doing a linearization around a control point and then training PID controllers with respect to this control point, or maybe multiple control points, and then you have to analyze which control point am I near, and my control policy is, do the controls analysis near this point, find the nearest point, etc. Right? Now, there has been a long time, for a very long time, there has been this goal of getting nonlinear controls into industry, right? And there's been, an entire academic world that has been focused on, can this be possible? And the answer, of course, has been yes for a very long time, but the tooling hasn't gotten there. And one of the reasons why the tooling hasn't gotten there was because nonlinear controls needs much faster ways to be able to do the simulation, because it needs to be able to run the simulator hundreds and hundreds of times during its nonlinear control, discovery or fitting process, right? Well, as I just described, we found the speed, right? This is what the surrogates and stuff are allowing us to do. And so one of the key applications that we've been building on top of these accelerated tools is a nonlinear controls library, right? Because that's the piece that can really make use of it. And so there's a video series to learn Julia for control. As I mentioned, if you go onto the JuliaHub YouTube, you'll find that there's a 10 video series. I think that the first 5 are out. It goes over everything from frequency domain analysis, PID controller design, but then to LQR, H infinity. So if you're really looking at like the details of doing a full controls analysis, Frederick does a really great job of walking through this. Each one of these, I think, is an hour long and shows you exactly the code that's being ran, explaining the code line by line. So please check this out if you're interested in doing controls. And so one of the big pieces that we've been focusing on with the controls library is bringing model predictive control to industry. So basically what we can do is models from ModelingToolkit or FMUs can be used as the input, and then we can take this to be able to train a model predictive controller with some robust techniques. Now you can do this, again, surrogates are part of the story, right? So you can do this with the linearization. That's pretty fast, right? That's pretty fast. And then you can do this with the nonlinear form, right? It's a bit slower, but then you can use a surrogate of the nonlinear problem and then with the surrogate of the model predictive controller, you can hit speeds that even outperform what we had with the linear MPC, right? So this kind of shows, one of the difficulties with bringing a model predictive control to industry has been that performance problem, but surrogates are really what's making this be possible for us. Now, a lot of what we've been focusing on in terms of making sure it's good for industry has been how do you handle uncertainty quantification, right? I mentioned before that you can begin to quantify your uncertainty in the parameter estimation process using virtual populations. But once you have a measure of uncertainty, you can use things like these robust control technologies, right? So robust control technologies, what they do is they don't try to find the answer that is, they don't try to find the answer that is the best. They're trying to find the answer that is good for all values, given that you know that your model is probably incorrect, right? And if what you're trying to do is fly a plane, you don't want to, find the value that is absolutely the, best answer if everything about this plane model is correct. You want to find the model that is most likely true, given that we know that the plane model is uncertain, right? And that's what this robust model predictive control is. It ties in nicely with our other set of tools that, give you a measure of the uncertainty, and then you can use this measure of the uncertainty to be able to then give you a good prediction about how you should be tuning your controller. So maybe, maybe if you had a very good estimate of what your internal, of the temperature in your room was, you would turn on your air conditioning, you turn it off at exactly the right times, right? But if you don't have a very good measurement of it, you might want to ramp up the speed at which, you heat, and you might want to ramp down the speed. You don't want to do everything bang, bang, on, off, and this is really the idea here, trying to find control policies that are taking into account the uncertainties that we know about. One nice tool to kind of be aware of with the controls library is that it has a PID auto tuning app. We have a lot of other tools that will be releasing apps like this as well, where you can tell it to boot up the PID auto tuning app. And you can then start to tune around, move around some of these knobs, change the discretization time, the simulation time, and then be able to see live updates on how your control policy would give you different solutions. Yeah, I see a question here. Can tuned MPC controllers be exported as FMUs? I believe so, and I need to go double check that. Please send this question to us, and we can respond. I believe that the answer was yes, because it is a parameterized modeling toolkit model, so I believe that you can generate the FMU. I don't know if we have a tutorial up for it, but that sounds like a very good thing to make sure we put as a tutorial in the near future. So yeah, thank you for that question. So if we don't have a tutorial for it right now, it is very close to, it wouldn't be difficult to do. So yeah. So the next thing is a structured controller tuning. So this allows you to, if you have a set of controllers or multiple controllers that need to be tuned in tandem, the structured controller tuning methodology allows you to handle this set of controllers and then make sure that it's once again robust against the uncertainty. And also some tools for model reduction. So I mentioned that we have surrogates. The model reduction is a little bit different. These are the classical model reduction tools. So if you are doing a classical linear circuits analysis or linear controls analysis, these kind of techniques that you would expect to be there, like using Hankel singular values and other linear model reduction techniques, these values these techniques are there. So for example, this is showing the balanced truncation technique for for linear model order reduction. So you can almost think about the surrogate techniques as machine learning enabled nonlinear model order reduction techniques. But the classical ones that you would expect to be there in a controls library are there in case that's what you need and are looking for. Yeah, so let me go into this example then. So Instron has been one of the groups that we partnered with. They've actually gave a talk at the last year's JuliaCon. If you have not seen Brad Carman's talk at JuliaCon 2021, I would say or last year was 2022. I would say definitely go check out that talk. He goes into talking about how this car catapult system, what the goal with the control policy here is to find out what forces you should be putting out on this piston, such that you push this car catapult at the correct forces. Right. What you want to do is you want to be able to say, take a video of a car crash and be able to recreate it on this platform, with the correct forces and everything, without having to crash a car. Right. If you could do that, then you can save a lot of money, because now you're able to, check safety features without crashing cars. And what was done was, instead of trying to be able to just tweak parameters, what you need to do is you need to find the forces here to push the forces here. And how it was done at first was someone would sit at a tuning computer and just kind of guess values, and guess up, guess down until you get something that looks about right. But what happened was modeling and simulation was brought into this. So that way, if you tune the model first, you find and let the model give you what the correct parameters are first, well, it's not going to be perfect. There's uncertainty in this world, but then maybe that'll be a better starting point. In fact, it was able to be a much better starting point. Though the way that they did this at first was using Simulink. They started this back in 2000, but as Brad mentions in his webinar, he was able to switch over to ModelingToolkit, where he got over 10,000 times acceleration. And with that, he's actually been looking into new control policies. And actually, this story is going to have a lot more to it in the near future, where this performance has allowed this model to actually become a lot more precise, and that precision is giving us a way to be able to find control policies to be able to eliminate actually a lot of other costs. So, stay tuned to hear more about what happens with the Instron case study in the near future. So last but not least, I want to go into some of these pre-made model libraries, right? So, we've had a lot of questions about FMUs, because, if you don't have a Julia model today, then if you don't have a Julia model today, then the FMUs are a great way to start using, controls, surrogates, and ModelOptimizer, right? But if you do want to start building a model in Julia, well, what are some tools so that way you don't have to build it from scratch, right? So first of all, we have the Modeling Toolkit standard library. This piece is open source. It's very similar to the Modelica standard library, but written in terms of the Modeling Toolkit part. It has mechanical components, electrical components, magnetic, thermal. So all these standard pieces that you would find in a modeling suite. So you can take these pre-built components, connect them together. It's what you would expect. And now on top of this, what JuliaSim has been focusing on is some very specific application domains that are kind of early users of the product, to ensure that, to help the growth of those industries with JuliaSim. One of those has been the JuliaSim HVAC library. I'll say that you should watch out if you're interested in HVAC modeling and thermal flows and such. Stay tuned for JuliaCon, where we plan to do a much bigger announcement with this. What we really focus on is the fact that in HVAC modeling, you have a lot of interesting dynamics, right? Things like two-phase flows, which cause the dynamics to be very stiff and nonlinear. And this makes a lot of model runtimes very high. And so we focused on building a library that is able to improve the numerical robustness, essentially, of some of the underlying pieces with refrigerant properties and such. So that way the simulations are then much more numerically robust, and then also it improves their performance. So we do have a webinar which goes into building a digital twin of a building model. It does not show everything that's in the HVAC system. It actually just shows a much higher thermal fluid model. But I'd say if you're interested in this kind of part, go check out that webinar. But also stay tuned for more details on stay tuned for more details on all of these things with two-phase flows and et cetera, because the components on that are coming out soon. We also have a battery library that's in development. There is you'll probably hear more about this in about April or so. There is a webinar that will be planned soon on the pre-built components for this. So you'll be able to, with this, you'll be able to take these components that have already been built for things like lithium-ion batteries and be able to put together a battery pack really quickly, and then be able to simulate that, and then run the model optimizer or surrogates on this model of a battery. We're also currently developing a rigid body library to be able to do things like robotic systems, turbines, and anything that requires rigid body systems. So that's kind of a quick overview of JuliaSim. So there's different pieces for different people. If you're trying to do some modeling, get in touch with us. If you're interested in HVACs, batteries, circuits, or rigid bodies. If you want to do one of these high-level tools, like say generate digital twins, generate surrogates, calibrate models to data, or do controls analysis. Even if you just have a Modelica model with an FMU, we're ready to chat with you on that. All those pieces are available. And then we also have specific apps. One thing I haven't mentioned is that we are building a graphical user interface. So that way, you can do the model development, drag and drop components, and then run these analyses on the generated model. That is, coming in the near future. So let me go over to these questions. What is the pricing model? Other than Julia and relevant domain knowledge, what prerequisites are there to use these tools? So the pricing model for this is a pay-as-you-go usage model. It's a cloud usage model. For exact details, I'd say talk to our sales team, which will go into detail about all the different pricing. But the key really is that when you go to JuliaHub, right, you get a window where you can make use of tools like the JuliaSim ModelOptimizer. So here, for example, I'm showing you I'm using the JuliaSim ModelOptimizer. I call this Stoke Global Opt, and it gives me a virtual population of size 50, and I'm plotting the uncertainty in the found parameters, right? Now, it's a pay-as-you-go model, and so here I'm using the JuliaSim IDE, and so would be billed on a per hourly basis right now. But talk with sales to kind of get exact details on that. So the next one is, does JuliaSim JuliaHub also have an on-premise offer in case data must remain localized? Yes, there is a on-premise kind of thing that is, talk with sales about this. I think it's called JuliaSim Air. And JuliaHub Air, so it's able to go on premise. We definitely have had this ask because if you've looked at some of our case studies, one of the users of pieces of this is DoD, or beginning to make use of this, and of course that requires it's not connected to the internet, et cetera, and so there's been pieces developed specifically to make that happen. They're not too out there on the websites right now, but if this is something that you need, please contact sales and we can talk in more detail about it. Does JuliaSim work with source control? Yeah, so JuliaHub itself has things to connect with source control tools with Git and such. JuliaHub has tooling for managing private registries, and so these all kind of connect together. I don't think with the window I have open that would be easy to show, but basically, yeah. I mean, the real thing is that JuliaSim is a Julia package. So, you just bring it in with the similar using an import statements. And as long as you're running on JuliaHub, the cloud, then you'll be able to access and use this code. And, the JuliaHub itself has tools to connect with Git. And so therefore all that comes as well. Ever modeled high purity, we can discuss in more detail. About the C3 distillation tower. That's starting to get into some pretty specifics. So yeah, please get in touch. We can chat and chat some more. Let's see here. Is consulting companies on use identification and development part of your offer? That's a good question. So is consulting companies on use identification and development part of your offer? I'm not entirely sure what you're asking here, but this is a good question to bring to sales. Can you mix rigid bodies and flexible bodies in one simulation? Yeah, so all of these model libraries that I'm mentioning, these are components for the modeling toolkit system. right? If you haven't checked out Modeling Toolkit, please do. This is this modeling system is free and open source. What you can do is you can just connect different components. So if you have a resistor, capacitor, etc., you can connect them. So if you use the rigid body library, but then you also use some flexible bodies, yeah, you just connect them. Does that what kind of simulation does that give you? That's a bit left up to the user. But what we will make sure to develop is a rigid body library that has basically the standard components of developing rigid bodies. And then if you do need to build a component yourself that's not in the library, that's completely documented how you do that. So please take a look at the Modeling Toolkit documentation. If you just search Modeling Toolkit, it should show right up. And in fact, if you want to kind of learn a bit more about how the libraries work, if you look at the Modeling Toolkit standard library, this has examples of using, say, library components. So say, building an RC circuit model by using what's in the Modeling Toolkit standard library electrical components. So, the rigid body library, battery library, HVAC library, they present themselves very similar to this. You just bring in the component library, you connect them to be able to build, say, a robot. But this also means that, you can connect the robot with a battery. All of these are on the same system. And we actually are very interested to see what kinds of extra modeling that synergy will allow in the near future. But yeah, it's all one system. So if anyone else, even open source, component libraries can be connected with the JuliaSim ones. So. Do you have any modules available for CFD acceleration? No, but though the surrogates library can be used on CFD, it's not specifically tied to CFD. There are some things that we are internally looking at that are more CFD specific, but I wouldn't, that's for a further future than the near future. So it's not currently on the roadmap. And I think that brings us a little over time. I guess I can answer this question here. Please send me more questions. If anyone wants to ask more questions, we're very accessible. If you message us at sales@juliahub.com, say if you give messages on JuliaSim, most likely they'll forward it around. And if it's technical, then I'll probably be on to ask it. So please make sure you just send all your questions. Always happy to answer them. What approaches other than surrogatization can break the 100 megahertz barrier or 100 hertz barrier on nonlinear predictive controls? Oh, that's a more technical question. I think that some of the things that we can do would be making use of parallel and time integration, making better use of SIMD. Yeah, so he's mentioning about how can we get this faster without resorting to some machine learning. Parallel and time integration, new integrator. In fact, we have new ODE solvers that are being developed at JuliaHub that can kind of do some of this. I'm not going to give more details right now, but they do kind of help out in this case. Yeah, I mean, there's a lot. So I would say that those are the two that are most promising. Though other techniques like those are probably differentiable MPC is also one thing that would be very useful there. New tools for doing randomized preconditioners and in convex optimization. Yeah, there's a lot that can be done. So there's a lot for accelerating MPC itself, and then there's also the machine learning aspects. We're looking at all these different pieces simultaneously in different subgroups of the team. Yeah, so I think that might be all the questions and all the time.
All right, then. Thank you, Chris, and thanks to everyone who joined us today. We will be sending out a follow-up email that will include a recording of this webinar, so you can view it at your own time. You can always reach out to us, like Chris mentioned, if you have additional questions. Have a great day. Thank you.
Yep, thank you very much.